So my name is Bill Buchanan, and I lead a podcast series in the World Leaders in Cryptography. And I'm so happy to have a true world leader with me today, Srini Devadas. Hi.
Hi, thanks for having me.
Srini is a Edwin Sibley Webster Professor of Electrical Engineering and Computer Science at MIT in the Computer Science and AI Lab. His current research interests are applied cryptography, computer security, and computer architecture. Srini was awarded a master's and a PhD degree in electrical engineering from the University of California at Berkeley under the supervision of Arthur Richard Newton. He was an inventor of physical unclonable functions, or PUFs, and in 2014 he received the IEEE Computer Society Edwin J. McCluskey Technical Achievement Award for the invention of PUFs and secure single-chip processor architectures. In 2018, Srini received the IEEE Circuits and Systems Society Charles A. Desoer Technical Achievement Award for the development of PUFs and enabling the deployment of secure circuits, processors, and systems. In 2021, he received the IEEE Cybersecurity Award for practice for the development of PUFs and the ACM SIGSAC Outstanding Innovation Award for fundamental contributions to secure processors, circuits, and systems. In 2016, he won the Everett Moore Barker Memorial Award for Excellence in Undergraduate Teaching, and in 2016, he was named a MacVicar Faculty Fellow, considered to be the highest undergraduate teaching award at MIT. So, what's your current role and what does a typical day involve for you?
I've been a professor here for 37 years and counting, and I have to say, it's been a pretty homogeneous life in the sense that my life really hasn't changed very much in the past 3 decades. I live in the same house, I go to the same office. I meet different people, but some of the people I meet have aged along with me, and then others are exactly the same age. I mean, they're not the same people, but they're the 18 to let's call them 30-year-olds. I have to say things change a little bit post-pandemic. I used to go in 5 days a week. Since I live about 15 miles away, now I go in 3 to 4 days a week. Get to work in the morning, meet some students. Usually, my class teaching responsibilities are 2 days a week, and those really anchor my schedule. So it's really all about preparing for class, getting done with class. Tonight, I'm going to give a quiz from 7:30 to 9:30 p.m. And so I'm going to be, at work late, proctoring the quiz and collecting, all the quizzes, and then I'll probably get back late. But that's not the most typical day, but it's a typical day. So.
It's really amazing that someone who is a true world leader in cryptography is also inspiring students. So it's great to see that. And obviously, MIT is really the home, you could say, or the foundation of cryptography. Reves, Shamir, Edelman, the invention of RSA, and so on. It has such history. Can you think back about the people you've met there? There must be so many
Oh,
amazing
of course, of
people.
course. I mean, I should mention, and I'm glad you brought it up, that I'm on the eighth floor of a building. It's called the Gates Tower of the Data Center. And on the sixth floor, it was really what you've described here with Ron Rives's office, Shafi Goldwasser and Silvio Micali, other
Yeah.
founders of the field of cryptography. And especially Ron has been absolutely instrumental in my education, really, in cryptography. I mean, I didn't start out in cryptography. I was a full professor at MIT. I joked that I couldn't spell cryptography, until I became a full professor at MIT because I was doing other types of work, including in computer architecture. And I took Ron's class. it's called applied cryptography now, but I think it was called computer and network security, actually, back in 2001. And that was the beginning of my exposure, relatively late in life, as you can imagine, to this beautiful field. And it's been amazing to, run down a couple of stairs or a couple of stairwells and go talk to the people who created the field, back 40, 50 years ago. So
That's fantastic. So what were your school days like? I appreciate that you came to the US when you were a little bit older. What were your school days like?
so I grew up in India. I grew up all over India. My father worked for the Indian Railways, which was really, I think, modeled after the British system, the British civil service. And so one of the things that affected my upbringing and childhood was moving every 3 years, from the south to the north to the east. And I went to IIT Madras, which is one of the wonderful school in India, in the south. The city is now called Chennai, but they haven't changed the name. It's still IIT Madras. And then as you mentioned, I came to Berkeley for graduate school. And then, so I've really only been in universities all my life. I'd say I call them the three greatest universities in the world. No offense intended. IIT Madras, UC Berkeley, and MIT. And so I come from an educated family. My father has a PhD, had a PhD, I should say. And my mother has also passed away. I had a master's degree in psychology. And growing up, it was really about doing well in school. I mean, nobody told me to get rich. Everyone said I had to do well in school. So I think that's kind of a summary of what my school years were like. And I feel like it's kind of a continuum. I mean, I feel like I'm the same person who grew up in India and came to the United States for grad school and then became a professor. My perspective, I think, hasn't changed very much.
No. You see the importance of education. I mean, you obviously have an amazing career, and it was all built on that hard work that you did at school and obviously in your undergraduate studies. So, what sparked your interest in mathematics, cryptography, electrical engineering? I did electrical engineering a long time ago too.
Yeah, I think it was pretty clear to me right from the get-go that I wasn't going to be a doctor or a biologist or experimental scientist, but I liked the analytical aspects of the classes that I was taking, and math was certainly a strong subject of mine. I loved it. I mean, usually the things that you love, you're good at, you work on them more, and so by the time I was in high school, it was fairly obvious that I was going to go the engineering route. And I think I was probably about 12 when I started buying, using my pocket money, circuit boards. And I think I built my first little radio. And built is too strong a word. Assembled is probably the way of putting it. But I remember showing my grandparents, the radio and with a little tiny little, single headphone earbud, and listening to some random the AM station or getting them to listen to it. And it was just, one of those moments which you don't forget, right? So I think Marconi was my hero, back growing up. So, we're certainly an electrical engineer, one of the founders of that field. And so then it was, almost obvious to me that I was going to try and do something in the engineering field. And I'll have to say that the aspect of electrical engineering that really I think attracted me was the wireless and radios and things like that. Computer science really didn't exist the way it does now. In fact, I couldn't major in computer science just because by the time I got to IIT Madras, or the time that I got to IIT Madras, they hadn't started an undergraduate program in computer science. They did it while I was an undergraduate, and I was able to take classes. So all my degrees are in electrical engineering, and But I ended up doing work in computer-aided design for my PhDs that was, really on the edge of EE and CS. And one of the reasons why I didn't start on cryptography until late was I was in the electrical engineering side of my EECS department. And then after I received tenure and when I was close to being a full professor, I moved to a different building, which was the building that housed the Devests and the Goldwassers and the McCallies. And so that was kind of the transition from, I'd say, being an electrical engineer to a computer scientist, and then getting into the world of computer security and cryptography. And that happened in 2000, 2001. So about 25 years ago. So
Yeah, and my interest was sparked also by joining an electronics club and building little radios and things like that. And I think it becomes magical when you actually see the components. These days, you buy a microprocessor that has 100 billion, 50 billion transistors on it.
That's right.
And students probably don't know that there are little transistors in there, tiny little
Yeah.
ones. At one time, you could actually see them. They had three legs. They were
Exactly.
NPN or
TTL
PNP.
components, put them on
That's right.
breadboards.
Yeah.
It's amazing. I'm actually teaching a class this semester that starts from transistors and ends at operating systems. We
Wow.
call it computation structures. And we just done with the class. I gave my last lecture on parallel processing a couple of days ago. So, yeah.
That's good. And your work is great because you actually work on the hardware interface, and that's where a lot of the security problems actually happen these days. So, as most people work in the high levels of operating systems and so on, you're actually right down into the silicon, which I think is quite fairly unique in your field. So, what topics do you teach just now? And I hate to say it, what's your
So
favorite subject?
yeah, well, that last one is a tough one. I'm not sure I'm going to answer that, but I mean, the first one is more about telling you how I've been a tourist. I think of myself as a teaching tourist and a research tourist. I go to different countries or teach different classes with a bunch of my different colleagues, and so let me say something that might surprise you. In my 37 years, I've taught 22 distinct classes. So ranging from algorithms to programming to computer architecture to circuits to computer-aided design, with maybe 50 of my colleagues. So we have this wonderful team teaching concept. I've taught with Ron Rivest. I taught not the class that he taught me,
Yeah,
but a class
yeah.
on introductory algorithms with him, several years ago. And then a few other faculty as well in the cryptography area, including Vinod Vaikuntanathan. It's a tough question to answer as to what my favorite class to teach. And, the glib answer is the one I'm teaching right now. I will say that the classes that are a combination of theory and practice, where we talk about elegant mathematics, perhaps moving into algorithms, doing proofs, and then people write code that corresponds to maybe a binary search tree or something like that as an assignment. I mean, we don't necessarily code in class. The other classes we do, but not the algorithms class. Those are the ones that I think ultimately, if I had to choose, it's like you got one more chance, Srini, to teach. What are you going to pick? And it'll probably be introduction to algorithms. So.
Yeah, yeah. I must admit, I miss teaching analog electronics. I, like you, have taught many subjects and have ended up with cryptography, but I do used to enjoy teaching transistor theory and
Yes.
NPNs and defect gates. I know technology has changed so much. So you obviously really enjoy teaching. What's your, apart from this practical side, which is obviously important, what's your general approach to teaching?
So, I mean, things have changed, I think, Bill, over the years. I mean, I think, we try to keep growing, as people, as professionals. I feel like, I'm a better teacher than I was, let's say, 10 years ago. And I think 10 years ago was better than what I was, 20 years ago. And I think ultimately, I think it's really, you have to have purpose for every lecture. Obviously you have a purpose for the class, but I think, on a smaller scale, you have to have purpose for every lecture. And I think what I've hopefully gotten better at is clarity of purpose. What is it that you want to convey? What is the concept? How simple can you make the statement of purpose? And then I think if you have that, that's kind of the basis of the entire lecture. And I think it's pretty dynamic. I mean, I don't rehearse. I mean, I obviously look at my notes and I prepare, but I don't rehearse. I think the spontaneity is important. I just think it's, I think, a little more engaging. It's, the Yeats quote, let's inspire, let's not fill the bucket. And I think that the danger always is you feel like you have to cover X, Y, and Z, in order for it to be successful. And what I'm really trying to do is to simplify that. It's just about X, right? And all the facets of X, and make sure that anyone who's in the classroom and has paid attention, is educated in some way. And I think that's the primary consideration. And I want them to be entertained as well, because I think that's an important aspect. I think the people who are entertained are engaged, and the chances that they're educated are much higher. So.
It's true. It's true. And basically, you have learning outcomes for the whole module, and you also have learning outcomes for the things that you're trying to teach in every single area. Right. And you try to wrap up, you try to provide the foundation theory, something that's interesting, something that's practical, and so on. And you are an entertainer to a certain extent. The best teachers are really entertaining people that inspire. And you must meet so many amazing students in MIT. Do you see, has there been a change in these students? Do you see them changing their viewpoints and the types of careers that they want? Do you still see that research is a career option for many?
Well, we get amazing students. I don't think there's any question about it. The two things that have changed, the thing that's a little bit more mundane, I should say, is the size of classes have increased. And I don't want to spend too much time on that, just because of computer science and algorithms have become so much more popular, and I'm talking about, the past few decades. The other thing that's changed that is the modes of presentation and the modes of learning have changed for the students. I mean, we give them so much more. We give them the PowerPoint, we give them the LaTeX, we give them the videos, we give them the audio. And that was never the case when I started. I mean, it was, you had to come to lecture, and then maybe you got a sheet of paper, and you got to take notes on the paper. But it's much more modern now, as you can imagine. But we still use the blackboard for some of our classes. Big chalk and lots of blackboards. This particular class that I'm teaching in architecture, there's so many diagrams, and there's so much complexity associated with the details of computer systems that we use a screen and project PowerPoint. But again, it's about what I'm saying. It's not what's on the screen. Pay attention to my voice, and then I'll tell you what's on the screen, right? But so I think things have gotten better in terms of, I think, technology. But fundamentally, it comes down to what I just said, which is focus on the concept. Have you gotten that across? And use the slides, or even what you write on the board, as a guide, and it's not the crutch. I think the worst lecture that I've ever given I would correspond to me using my slides as a crutch, right? And then at that point, it's like, what did I contribute? Well, probably not very much. I mean, if a student had read the slides, they've probably gotten most of what I said, right? So that would be a failure on my part. But I think the other side, the success would be everyone in the room walking away with thinking that they've learned something, right? It's
yeah. I must admit, I miss the days of chalk and blackboard. I used to really enjoy drawing things. It's not quite the same with whiteboards anymore. I think it provides a little bit of interaction and a little bit of spontaneity.
Yeah, no,
overall.
exactly.
So you were the inventor of PUFs. These are physically unclonable functions. Could you just outline how they actually work?
Oh, of course, of course. I will say that the concept predated my work, and we focused on silicon. So I think one of the interesting things about puffs is, they're potentially, naturally occurring objects. And you can think of a crystal, that is being generated by nature as being a puff, and then you could try to use it in a security setting by saying it's an unclonable object, it's unique, and you can take pictures of it from different angles, and then later, identify it or authenticate it. And I think, well, our work was potentially the first work to realize that you could build circuits in silicon and rely on the inherent randomness and variation in the silicon manufacturing process. And assuming that you would build the circuit correctly, the same design, when it was fabricated on different pieces of silicon, would come out a little bit different. I mean, we're building skyscrapers on silicon, right? I mean, there are a number of layers, and this with your analog and digital electronics background. And so these skyscrapers are a little bit different. You built millions of them, and each one of them is a little bit different. And I think the realization was, rather than having a separate measurement device like a camera that was looking at this crystal and then trying to identify and authenticate it, you could have the measurement circuitry and, of course, the puff itself, the gates associated with the puff, in the same piece of silicon. So you created the circuit that was producing from digital inputs, producing digital outputs, and you can predict, what the response would be for chip A, even though you'd seen chip B, which was the same design, and chip C and chip D, and any number of chips. And so really the original name for this was physical random function. And but PRF, as is an acronym that stands for pseudo random function, and it was already taken. And so we decided it's also hard to pronounce, so we decided to call it, in addition, PUF, and that's the name that became more popular. And I think that was a good move on our part, to call it something pronounceable and something different from pseudo random functions. But that's the basic idea, and my students and I had the idea in I think 2001 or so, and we were building things on silicon, thanks to the fact that we were electrical engineers for the most part by 2002, and I'm quite surprised as to how long-lived the idea is. Most of my ideas haven't stood the test of time. So.
Yeah. And when I remember doing VLSI design, it wasn't we talked about microns. That's a millionth
Yes,
of a
yes,
millimeter.
yes.
And now we're down to 5 nanometers. I may be wrong in this. I think
No, you're
there
right.
are
You're right in this.
certain factories that are. Did you ever think we'd get that small? I mean, obviously there must be a limit to we're down to just a few atoms
Well,
in size. Do
atoms
you
are
ever
supposed to
think?
limits. Yeah, yeah. No, I mean, what was amazing to me, Bill, was it was actually the realization that the silicon, the dioxide that is under the gate of a transistor was only hundreds of atoms thick.
Wow.
Right? It's the microns are one thing, the nanometers are one thing. And obviously, nothing it contradicts what you just said. I mean, it is amazing.
Yeah.
But the fact that the dielectric is hundreds of atoms thick and is getting thinner, that to me was amazing. And I remember people talking about single molecule transistors and things like that. And a single electron going to turning on the transistor or turning it off. I guess, eventually I maybe, probably not in yours or my lifetime, Bill, but, we'll get there. But Moore's law was, certainly alive and kicking, back in early 2000 by 2005, 2010, I think people started worrying about running out of room, shall we say. But, I'm amazed at how it's continuing. I mean, it's obviously, billions and billions of dollars. Every design generation is more expensive, but I think we'll get to sub-nanometers. I don't know how much further we'll go, but I'm super impressed with the manufacturing folks as to how long-lived Moore's law has been, right?
Yeah.
So.
And your PUF methods basically revolves around having perhaps two signals that can race each other. And on the
Yeah,
way, one of the signals gets slowed down a little bit, has more resistance and capacitance and so on. And I think your approach was that every chip will vary slightly in those paths that were involved. So what happens when a PUF when a device changes its ambient conditions, like it gets hot or
yeah.
cold
No,
or
that's a
bent?
great question, and we grappled with it. We grappled with it. So the general, shall I say, a paradigm that we rely on is exactly as you said, a race condition. And the race is something that corresponds to, this path has greater delay on this chip than this other path, that's adjacent to it. And we were very careful about laying out the circuit so the paths in the design were exactly the same length in the design, and a manufacturing variation it makes the paths of different delays, right? I mean, and in fact, even potentially of different lengths, slightly, in the scale of let's say nanometers. And the ambient conditions, do control the voltages, the temperature, the specific voltage that you apply. It controls the delay of both of them. But the robustness comes from the fact that we're measuring relative delays. And so when the temperature increases, a delay increases as well. And the idea is that path one increases in delay and path two increases in delay. So there is an inherent robustness with path one at a higher temperature still being, let's say, faster than path two, or in a different situation on a different chip, being slower. And so there's it's not the case that you have very common flips. So a flip would be that you change the temperature from 0 Celsius to 20 Celsius, and the path that was faster became slower, right? It does happen, but the percentage of time that happens for a particular chip and let's say pairs of paths is more like a few percent of the time, as opposed to being 50% or much more, much more than that, right?
I see. And the application of this is massive. So you must see lots of applications of your invention in current devices. Do you have a few examples of where it's been used?
Yeah, well, I mean, there's two classes. I think of this as a silicon biometric. It's a biometric like our irises and our fingerprints are biometrics. But one of the advantages is you can make the circuit as big as you want. So I joked, back in the day that imagine that I needed to authenticate a person, and the person had as many fingers as you wanted, right? You could have 100-fingered person. I mean, the entropy in our fingers isn't that much. It's about 10 bits per finger, and it doesn't scale with the number of fingers because your finger and my finger maybe are 10 bits apart, our thumbs. But given that we have compared our thumbs, our index fingers aren't 10 bits apart, right? So, but with silicon, you can make the circuit as big as you want, and you can do as many of these races as you want, as we just discussed. And so you could get enormous entropy. And so it was really, a biometric with as much entropy as you wanted, right? And so we initially thought that we would have a very cheap way of authenticating circuits and supplying the semiconductor supply chain. And we also, built RFIDs that could be tacked on to products like luxury items like perfume and wine bottles and things like that, where we said we can authenticate products. Now, of course, what you're doing is authenticating the silicon, and the silicon is embedded in the product. But your important part is it was an authentication application. So, there was certainly some of that. I bought a Canon camera, or I should say my student bought a Canon camera in a Chinese supermarket, back in 2014, where the package, as it turns out, of this Canon camera had an RFID tag that could be authenticated using your Android phone. And so you could, obviously, you could, open up the package and put a counterfeit Canon camera inside of it. And so there's a tamper evidence seal for that. That was separate from the PUF technology. But the fact that there was a PUF RFID on top of a Canon package, was certainly something that I was thrilled about. And I have exactly that Canon camera outside my office, for everyone to see. Not the camera, but the package. So that was one class of applications. But the other class, I think, is really, in some sense, more appropriate for our podcast. It's producing secret keys and for cryptography. I mean, all cryptography relies on secret keys. And you could imagine producing a unique secret key from a piece of silicon. And I'm fond of saying that no one knows what the secret key is other than the silicon itself. And so it's a piece of randomness that you could use to do lots of wonderful things that the Ron Rivest and the Shafi Goldwasers of the world have taught us to do. So, and I will say that the second class of applications is certainly more common than the first class. The key
that's
generation.
Fantastic, because obviously what you can do is you can create a non-interactive zero knowledge proof, or more commonly a digital signature from the device using its private key that you see is generated within the device to do with its silicon.
Right.
So that's an amazing concept, that every device would have its own unique private key that wouldn't be in a secure enclave. But we'll come back on to that in a little while. So what do you think the research gaps are in PUFs just now? Because this isn't it's a fairly mature area, but there are still many
I would say
issues.
so. I would say so. I mean, when you have silicon in products that are deployed, you need a level of maturity that certainly wasn't there when we were thinking about these things 20 plus years ago. So that's certainly gratifying. I will say that I think some challenges with PUFs have been in the authentication space and integrating the circuits with all the circuits that are out there. I mean, the ideal situation really is you got a processor, it's a billion transistors, it's tens of billions of transistors, and you've put a PUF inside of it that allows you to authenticate that the silicon came from, let's say, TSMC. Or you put a PUF inside of it such that it's produced a private key, and then the public key is put out, and obviously that public key has to be certified by a VeriSign-like authority. And so I think there's challenges there. That process is not as smooth as I think it needs to be in order for it to be pervasive. And so there are companies who are working on things like that. I've certainly, I'm someone who likes prototyping and producing ideas, and then let's let the professionals in industry figure out the deployment challenges, right? I never thought of that as being something that I'm responsible for, right?
Yeah. I mean, I suppose a blockchain solution is obviously the other approach that we're seeing it with RFID types of devices, where you can register the public key onto a blockchain. But as you said, you could use a PKI type system there too.
Right.
So I think you published a paper on a universal cryptography accelerator. Could you tell? Because there are so many different things in cryptography. There's obviously public key,
absolutely,
hashing, symmetric key. How would you make a cryptography accelerator?
Yeah. So, as I mentioned, I've done a little touring here, Bill, in the field of security and cryptography, and you mentioned secure enclaves, and maybe we'll get to that. But that was sort of the next thing after PUFs. But soon after working on secure processors, it was kind of obvious that we wanted um, sophisticated cryptography, beyond encryption. We wanted Merkle trees and integrity verification of memory in processors. And then, there was an explosion of interest, partly because of blockchain that you mentioned, but also because of fully homomorphic encryption and the fact that you could do encrypted computation. And all of this was happening in, like the 2010 to 2020 timeframe. There's this tremendous explosion in sophisticated cryptography and the need for deployment of these much more sophisticated primitives than let's say basic encryption. So as a hardware person, I do love building prototypes, as I mentioned. I started looking into how fast or how slow these protocols were. And they're magical in one sense and completely undeployable in another sense. Case in point, if you want to do a computation on computing your taxes, and let's say that that happens virtually instantaneously on your computer because it's adding a bunch of numbers. Well, if it's going to be a billion times slower, then maybe your taxes are okay because instead of taking nanoseconds, they take a second. But if it was going to take seconds to do a computation, you don't have a billion seconds to wait, right? So I realized that there was an opportunity to apply hardware speed up, hardware acceleration, and one of the biggest challenges, and now I'll answer your question, to building hardware, especially complicated hardware and it needed to be complicated because the protocols were complicated. Is how useful is this? How general purpose is the hardware? The most common chips in the world are programmable, right? So building a chip that could only do homomorphic evaluation of your taxes, or maybe just doing a zero knowledge proof, I felt wasn't as compelling as saying, here's this engine that is going to accelerate whatever cryptography you have that you're interested in, be it a ZKP, a zero knowledge proof, or an FHE engine. And we haven't built this yet, but that's kind of the concept of a universal cryptographic accelerator. It'll accelerate these highfalutin cryptographic protocols for you. And the motivation behind the universality is exactly what I said, which is the chances that someone is going to drop tens of millions of dollars in building a chip is going to be proportional to the number of chips that the person thinks that they can sell, right? The capital cost is so large that you have to have a way of raising the numbers, the potential profit. I mean, it's the straight, mercenary argument. You drop 10 million bucks. When are you going to get it back? When are you going to get back, 100 million, right? And so the universal cryptographic accelerator is an economic construct in the sense that the cryptographic acceleration is a technical construct. Universal cryptographic acceleration is, I would say, much more of an economic construct. It's driven by economy. So,
and I suppose Nvidia spotted the opportunity where Intel didn't quite. They were still doing their plain old CPUs with 64 bits of registers, and we're dealing with thousands of bits in there.
Well, I mean, Nvidia, I think built their processors for graphics. And at some level, you could argue that they're the luckiest company in the world, in the sense that they realized that everyone realized that vector processing and tensor cores were helpful for deep neural nets and transformers also, right? So I'm not going to give them the credit for realizing that. That vectorization was useful for machine learning because they'd already done vectorization, raster scanning, and all of that for graphics, but I certainly give them enormous credit for morphing their architectures over the past 10 years to better accelerate, all of the things that people are interested in right now. Coming to that, I'm doing some work, at the moment, submitting a paper in the next week or so, where we want to do something that you love, which is incredibly basic. So switching away from universal cryptography, A times B mod P, Bill. I would say that is a fundamental operation to number theoretic cryptography, right? Modular multiplication. Well, it turns out that you can, and this is work that was done in 1995, it turns out you can use the residue number system, and even though P is a prime, you can pretend that you can choose a composite modulus, and you can use vectorization to speed up A times B mod P. This is not our work. This was Posh and Posh in 1995. What one of my students, Simon Langowski, has done is taken the variants of Posh and Posh and figured out a way of using AVX, which is the vector instructions in CPUs, and all the way to tensor cores to do this RNS calculation with, I would say near perfect speed up. So now you have a prime that's this huge RSA prime, which obviously can't be factored, but you can pretend that you're actually doing A times B mod a composite modulus, thanks to these algorithms, and then break the composite modulus up into much smaller primes that are all about 32 bits, and then use all of this parallelism that you have to speed up a single modular multiply, right? I think this could be a different way of thinking about universal cryptographic acceleration. So here's the other side of it. Let's accelerate the most fundamental primitive, corresponding to number theoretic cryptography. And if you accelerate that, you've accelerated all of number theoretic cryptography. So you're coming at the problem in a very different way from what I described to you, which is building a programmable accelerator that accelerates FHE and ZKP, right? But
that's right, because even homomorphic encryption requires the mod P
even homomorphic
operation.
encryption requires, that's
homomorphic encryption. So it's so fundamental, as you said, because you've got to constrain your numbers into a finite field. The way you do that,
you only have 32 bits.
Numbers.
In fact, these things have 8 bits and 16 bits, and you're trying to get more parallelism. The other thing that I think the GPU folks realized was, you can think of 128 bits as being a single operation of 128 bit numbers, or you can think of it as being, let me get my math right, as 8 parallel operations of 16-bit numbers, right? And so there's 8x parallelism if you have smaller numbers, and they exploit that. And in some sense, this work that I just described to you, the modular multiplication speedup exploits that as well, right? So
and Intel know this well, because if you run a test with AES encryption, you'll actually find it's faster, even though it shouldn't be faster than, say, Cha-Cha-20. It's because they've built in all of this extra functionality
because they put that into the silicon. They put that they put AES into silicon. And I think hardware acceleration of these basic primitives has changed the way cryptographers think about using these primitives. They think about PRFs, pseudo-random functions, as being AES, or implemented using AES, because AES was built into hardware, and it runs faster than a software implementation of perhaps a simpler pseudo-random function. But that software, it needs to be fetched and decoded and executed, and so that takes a little bit longer than the piece of silicon that has the XORs, feeding each other, so to speak, right? So hardware is a powerful, I think, a mechanism. I mean, well, it's fundamental in the sense that you have to have it to run software, but I think it can change things at the algorithmic level because it changes the trade-offs.
Yeah, and I think even Samsung have released their new phones, which actually have post-quantum cryptography chips built into, because they know they have a life of maybe 10 to 15 years, and they're actually going to see the rise of post-quantum cryptography, so they need to support that in some sort of way. So it's obviously a changing landscape, but eventually it needs to come down to the silicon. So how do you accelerate a zero-knowledge proof with hardware?
So the algorithm itself obviously is way more complicated than modular multiply. But if you take something like Groth 16, which is really the most popular ZKP that's out there, it's got elliptic curve signatures inside of it. It's got pairings, and it's got modular multiply inside of it. I will say that there's Amdahl's law, which basically paraphrasing a bit says something like if you only accelerate 80% of your computation, but you accelerate it infinitely, you're only going to get a factor of 5 speed up because your 20% is the same. And so the challenge with the more complicated protocols, Bill, is Amdahl's law, which is you can't ignore anything. And you wanted your 1000x speed up. I mean, the whole purpose of building hardware was to speed things up very dramatically. So if you want your 1000x speed up, you can't ignore even 0.1% of the computation, right? So it's really, you got to be super careful. You got to look at the entirety of the algorithm, every line of code of it, and you got to figure out how each line of code is vectorized. And the beauty of hardware design for ZKP acceleration is, I mean, you are a painter. You got this giant canvas, and you can choose your execution units, the number of them, the functional units. You got this funky XOR operation that adds an AND at the end of it. Sure, put an XOR gate and put an AND gate in there, right? So, so in that sense, you have tremendous freedom, and that's actually something you absolutely have to exploit. If you don't do that, there's no hope. So I would say it's you have to think about the operations and produce the exact functional units for those operations. The other big thing is data movement. One of the things that CPUs are not very good at, even if they had the functional units, is what happens when you have a chain. How does the output of the first computation get to the input of the second? And does it have to be transformed? I mean, are you doing convolution? I mean, a lot of these things, NTTs and so on, do convolutions. Well, convolution is not something a CPU is particularly good at, or actually, to be honest, not even a GPU. But you could build the exact data network or the communication network, a permutation network, a convolution network in silicon. So the wires are essentially there to do this in a perfectly efficient fashion. So not just the functional units, the other piece of it really is the data movement has to be done exactly right. And one of the things we discovered was permutation networks were really important. And having the right permutation network would take care of the data movement problem. And then choosing the right functional units would take care of the speeding up the operations problem. But that, I think, in a nutshell, is the way that you accelerate, ZKPs or FHE. Carefully look at the algorithm and then look at the movement of data and the computation. I mean, those are the two big things, right?
Yeah, that's right. Because so you've obviously got pairing-based cryptography, so you're moving from a software implementation into hardware for that. You've got, as you said, your segmentation, things need to run at different speeds. You have different clocks. It's like with a CPU. The clock that's on the motherboard is running a lot slower than the clock that's actually on the chip. So I suppose you've really got to understand what clock speeds that you have and understand the physics of the chips inside.
And if you have things that are running slower and you can parallelize, then if you could try and make up for that by having parallelism and doing these operations. The latency is long, but the throughput becomes less because you have parallelism. So you match, as you said, the speeds, because otherwise you're waiting, and if you're waiting, you're dead. You wait a little bit, your 100x speed up is now 10x. I mean, you lose a lot, right? And so you can lose a lot very quickly. And so the care that you need to take for these sophisticated applications is really, I think, the crux of the matter. That's paramount.
Yeah. And obviously we need a place to keep our secrets, and we need a place to keep things secure. That's typically a secure enclave on a device or in the cloud, where we can keep our private keys and our symmetric keys and things like that. So can you outline how the Intel X, I know it's a complicated system, how the Intel SGX extensions work on processor architectures?
No, absolutely, absolutely. So it's going to take a little bit of talking here.
That's
I do
fine.
want to connect it up to PUFs just
Yeah.
for just a couple of seconds, really, which is, you have the secret key. The reason it exists is because you want to do a signature using the secret key. Maybe it's a private key, or you want to encrypt or decrypt, I should say, if it's a private key. And so that is functionality, that's computational functionality. And you can't allow that functionality to leak the secret. I mean, you have to do that signature algorithm without giving away the private key, of course. And that is typically the first thing that an enclave does, which is attest to the fact that you're running on a particular computer. And SGX does that, right? SGX is going to go through an attestation mechanism that tells Bill Buchanan that an Intel machine in the cloud that was built by Intel is running the software that Bill wants to run. So that's sort of the attestation mechanism is related to what we just discussed and what we've discussed earlier. And now the other part of it is, which is also part of the attestation, but a slightly different part is, you've decided that you want to run a particular computation. Let's say that you want to compute the millionth digit of pi, and you have your program that is going to compute that, and you've sent the program over, and it's just going to run, let's say, autonomously inside of this enclave. And you want to make sure that the number that you get back, we'll call it 7. I don't know if that's the correct number, is correct. And so you want this integrity attestation, integrity proof. And so the other thing that SGX and this secure enclave does is it sets up the environment that corresponds to this particular program that you've written that is running. And usually the program would have an input. In this case, let's just say it was autonomous, but you could certainly have an input. And that input came from you as well. It is measured. So you literally take a cryptographic hash, call it a SHA-256 hash, of the environment that essentially created the secure enclave that not just corresponds to the hardware, but the software that you sent and the inputs that you sent. And this measurement is part of the attestation that is sent back to you. And so you can verify that you're all set, with respect to your program has been loaded into this Intel certified enclave with your inputs, and then you say, okay, ready to go. And then you start, and then it runs, without being interrupted, because you got to be careful about things like that. And then produces the number, we'll call it 7, and it signs the number 7, using its private key, which of course has to be done inside of the enclave, and then sends it back to you. And you have the public key of Intel, which you've gotten from before. And you can verify that this 7 was computed correctly. So at a high level, that's how SGX and secure enclaves work, right?
I suppose CPUs grew up. I don't know if you remember the 4004 series,
Yeah, no, I do.
first microprocessor. I think it was Gordon Moore who actually created that one too. And then it was the 8-bit ones, 8000, 8080 and so on, then the 16 bits and the 32 bits. So they've kind of grown up without any trust, without any need. And it's almost like if we started again, we'd actually start again with something like the SGX infrastructure. I know in the UK they're pushing some silicon for trusted architectures. And ARM do you think ARM is generally better at this than the Intel architectures?
So ARM had Trust Zone, which was as old as the TPM technology, Trusted Platform Module technology, and I think that ARM and the combination of ARM and Apple and the Apple Secure Enclave, I assume uses a basic ARM processor, is a wonderful design. I mean, I teach that. I think they've been very careful. It's a slightly different problem from remote cloud attestation in the sense that it's also probably more challenging in some respects. You leave your phone locked, and even the FBI or MI6 or MI5 or whoever should be able to get hold of your data, right? So it's protecting the consumer on one side, as well as protecting the software. And so yes, absolutely. I mean, I think you need to treat security as a first-class citizen when you build your design. And I think Intel, certainly tried to do that with SGX, but given the complexity of the Intel processors, they had to tack on extensions. Now, if you could start from scratch, maybe it's not an extension, maybe it's a core part of the ISA, the instruction set architecture. I mean, I do think that as a purist and as a researcher, that would be the better way to go. So I would say let's start from scratch, right? So I agree with you.
Yeah, it's difficult. It's difficult to actually just reset. Microsoft have built a business on legacy and also Intel, so it's really, really difficult. Yeah. So you touched on this earlier, but what's the best way to keep a secret or private key on an integrated circuit?
There's the two technologies. I have to say that secure non-volatile memory, in smart cards is still the most popular technology. People worry about the fact that you can go to a laboratory, experimental laboratory or something with lots of equipment and extract that key from it. The other way is to use a PUF, and certainly for it's a volatile key that the bits would go away when there's no power, and the idea is that you could maybe create tamper resistant circuitry around the PUF to basically destroy the PUF. So there's research. I don't know how much of this has been deployed, Bill, but you could imagine getting a very highly secure key storage using a PUF and using a tamper detection mesh. And there's certainly been lots of research in this. I think it's classified, beyond a certain point, the research becomes classified and you don't get to hear about it. But these are things that are ongoing. And if you go to the Department of Defense, GOMAC Tech, for example, there's usually, a session or a paper or two in every conference on this type of work. So I think the most popular way and the easy way is to do the secure non-volatile memory, I think, deployment. But just because I like PUFs, I like the idea of the highest secure, the most secure solution using PUFs, as you can imagine.
Yeah. Every single thing on the planet has a unique signature and a unique private key. Even humans could have chips that identified them.
That's right. Yeah.
So obviously RAM has been a general problem area when it comes to cybersecurity, because it all ends up in ones and zeros, and it all ends up in memory. And software engineers aren't very good at obfuscating their programs. So if you want to search for a password or a key or something, you just do a dump of the memory. So I think you worked on oblivious RAM. Can you tell me what that is and what the applications would be?
That's right. So the work came out of the secure processor work. So again, to connect things up, we went from PUFs to secure enclaves, and then we started worrying about what happens when you leave the secure enclave and memory is not part of the secure enclave, and memory is this giant thing that you need to store. And obviously, the first thing that we did in the secure processor was to encrypt the memory. And so that was number one. And then the second thing we did was, if people could tamper with the memory, we overlaid a Merkle tree or integrity verification trees on top of the memory. So that was step two. And then step three was the realization that you could be exposing your secret through memory address patterns. And so you were accessing the memory. The addresses are unencrypted. The data is encrypted, but the addresses are unencrypted. And you could be accessing these locations that are encrypted in terms of data, but you could be giving away something about your program. The fact that you're computing the million digits of pi, just that might be the secret. You could give that away because of the access patterns. So then we looked at ORAM, and ORAM had been invented, decades prior. And we said, oh, goodness, we can't imagine building an oblivious sort, into the silicon, because that would just blow things up. And maybe you could do it now, but certainly, back in the 2000s and the 2010s, we couldn't. And so we decided we would look into building a more efficient oblivious RAM. And thanks to collaboration, we came up with a very simple oblivious RAM algorithm that literally the title of the paper is an extremely simple oblivious RAM protocol. We called it PathoRAM, and we built that in silicon. And I think it was almost certainly the first silicon implementation, direct hardware implementation of oblivious RAM. And the only reason we were able to do that was because of the simplicity of the algorithm. And so that took care of sort of the final step, if you will, of building a secure enclave that wasn't going to leak, even though it was touching memory, which is basically memory that just stores encrypted or unencrypted data. That was nice. It was a nice capper to this entire stream of work, getting to the point where we raised the security of the enclave, if you will, right? So.
Yeah. So I suppose this is all part of building physically tamper-proof systems. So apart from all the methods that you've talked about, what are some of the other guidelines that you would say the designers should be using to make it tamper-proof?
Yeah, so I think the big question is, do you have physical attacks or don't you, right? So what I've talked to you about, I think so far, it really, if you disallow physical attacks and you only have a remote attacker, then the only thing that's left is bugs in your enclave implementation, and bugs in the software. You need some software that attests and does the measurement, etc. And the idea is that you try to preclude those by a process of formal verification and things like that, right? So you build security against a remote attacker. Now, tamper-proof, I think for the most part, could involve both the remote attacker and as well as a physical attacker. And I think that's a different ball game. We touched upon it a little bit about how does one protect the secret key, but there's other things you could do. I mean, you have to worry about fault injection attacks. We actually thought about, and SGX I think also followed this this threat model where the operating system is potentially malicious because it is being compromised. And so now your operating system is a very powerful, privileged piece of software. And so it can do things that can tamper with the memory. That's partly why you need integrity verification of memory that is built inside of the enclave. It can look at the memory address patterns, another reason why. And effectively, the operating system being malicious is getting close to a physical attacker. I mean, it's not quite there because a physical attacker can start delayering your chip and do chemical etching and things like that. I think in a cloud at Amazon, I mean, given that this is, over, I don't know, in Idaho somewhere with perhaps a, policeman, outside, it's less likely. But, but cold boot attacks where someone walks away with the memory and looks at the memory contents, are things that you have to worry about. So I will say that you have to summarize, figure out your threat model, figure out the power of your physical attacker. It's a little harder to do that than for cryptography and for the computational side of things. And then depending on the power of your attacker, you got to add more defenses. And then the ultimate would be, having this this tamper mesh that you've seen in movies, which are raised, effectively, encapsulating the entire chip, where you try to put a probe in and bang, maybe the chip destroys itself, which may not necessarily be something that's tenable, but it should destroy its secrets, or it should protect the secrets that are running inside of it, right? So I mean that's almost sci-fi, but that's where I would leave it.
It's happening with Gen AI and obviously autonomous agents. We will have to have a kill switch. Actually, I know that
good point.
You presented a talk recently about data privacy in an area of AI and Gen AI. What was the main findings from that?
So there were many aspects to it, and so it was privacy, and obviously there's integrity and and hallucinations and making sure they don't AI doesn't hallucinate, and I don't work on that. But from a privacy standpoint, some of it was just confidential computing, everything we've talked about. You have training data that's secret. You want your model to be proprietary. you'd like to sell your model, but you don't want to give away the parameters. Well, people use secure enclaves and confidential computing on GPUs. The GPU now has a secure enclave. The H100 has a secure enclave. And so you could do confidential AI to protect your data and your model inside of an enclave. So that's kind of the easy, I think, aspect to it, or at least in terms of describing it, given our conversation. The other side is I think, so what about the query itself? I'm going to send in my query, and I don't want the world to know what I'm asking ChatGPT. One way theoretically would be we'll do fully homomorphic encryption on the query, but that doesn't work because of even if you had hardware accelerators, because it would just be too slow. But you could use a secure enclave there and SSL in and encrypt your query and get your responses back. Or you could do things like multi-party computation. Split your query into two parts. So that was really some of the things that I was talking about. I'll leave it at I think very challenging problem, partly because the computational cost is so large that the overheads have to be small. And I can certainly imagine secure enclaves being kind of the technology of choice to obtain confidential AI, right?
Yeah.
I mean, there may be some combination, like I said, a combination of multi-party computation and secure enclaves.
Yeah, and I think we really need hardware acceleration for homomorphic encryption. We're starting to see it, and I know that you can use machine learning with homomorphic encryption, such as with SVM, and I think you can even use back propagation with a neural network with homomorphic encryption. It's quite difficult, but it'd be an amazing world that we could actually train on encrypted data overall, because it's a big weakness. Yeah. So how do you build memory integrity verification and encryption for a secure processor?
Yeah, so I will say that we did that before we did our oblivious RAM work. So it was a stepping stone. It's really about looking at the algorithm. Encryption, it was about putting it in hardware is about speed. And one of the things that we had to worry about was you don't want to wait. I mean, it takes a long time to get something from memory. And if you want to add to that delay, it's just not palatable to the hardware architect. And so we used, counter mode encryption, and which hides the decryption latency. So that's a nice way of pre-computing what your decryption pad is. So that was one thing. Integrity verification was one step more complicated, and we used the standard algorithm. But it turns out that rather than going through the entire path of the Merkle tree path, you could cache, intermediate hashes, and we could speed things up. And so we wrote papers on this, 20 years ago. And then I've mentioned oblivious RAM, which was, another step after that. But that's really, I think, what it came down to, which is carefully looking at the cryptographic technique and making sure that you didn't slow things down, without realizing that you were. And building things is a great way of realizing, all of the things that have gone wrong, because you have something, you have an artifact, and then you run it, and you're like, whoa, what happened, right? So.
Yeah, that's great, because I know that in encrypted RAM you have the CTR. AES CTR mode, where you have the counter for each block, and you can make it parallel, and it can run much faster than if it was sequential. And so what's time travel optimistic concurrency control?
Yeah, well, that's a catchy title. It's a catchy title. No, nothing to do with cryptography, Bill. So I'll be brief. So I do work in computer architecture that has nothing related to cryptography or computer security, for that matter. And I was very interested in the cache coherence problem, which is you have lots of caches across different cores. And how do you make sure that one processor, a thread, for example, of the same computation isn't reading stale data? And then there's consistency, which is basically correctness of execution. And concurrency control is similar to cache coherence. It's in the database world. And the fundamental notion of correctness is sequential consistency or serializability, which are equivalent notions in two different communities, which basically says, if I have a parallel computation, it should produce the same result as if I had a single processor running an interleaved computation, right? So you do something, I do something, you do something, I do something, as opposed to us doing our own things and not synchronizing. And so one of my students, who's a professor at Wisconsin-Madison, Shangyao Yu, invented an algorithm that used logical time as opposed to real time. And I won't bore you with the details, but there was a step in the algorithm where you jump ahead in time, instantaneously. And that's why we called it a time travel. And you jump ahead, but in kind of I will say, a deterministic way. And you had to do a proof that the jumping ahead didn't violate, the sequential consistency of it. So it was a challenging exercise, and smart students figured it out. And so we wrote a paper with a catchy title.
That's great, yeah. Obviously, every researcher possibly has to make the decision as to whether they'll have something that's groundbreaking. So you could have done it with PUFs and patent it before they publish, or to go and publish and maybe lose the opportunity to license and to create a spin-out company and so on. And Ron Rivest is a great example of that. They patented, MIT protected. There was a lot of pressure. As I remember, it was published in the Martin Gardner Scientific American Post, and they said send a stamped addressed envelope. And I don't think there was some people in law enforcement that were very pleased about that they were sending these secrets across the world. But they patented, and they obviously created their company. MIT supported them. Whitfield Diffie and Marty Hellman perhaps weren't as lucky with their great invention. Perhaps the different university culture played in there. So some things have been held back. RSA wasn't held back. SNOR signatures were certainly held back. And only now we're seeing DSA being produced. DSA, I think the DSA digital signature algorithm paper was assigned to the US, the citizens of the US. So there's no right answer to this, but what's your opinions on patenting cryptographic methods? A good thing or a bad thing?
I think it's a personal choice. It really, I think would now go to the point where, or I would probably put everything in open source for maximum impact. Just unencumbered technology. Just because I want academic impact and I want deployment, and I feel like that's the path of least resistance if you want that. I think it's a little bit more complicated now than it was, back in 1978, given the competitive technologies that are out there for various things. And so you have a patented Schnorr signature, or you have a patented what have you, and you're trying to say that this is better than the next thing. I mean, if Groth16 had been patented, would it have been used in blockchain in the way it is? So I do think the world is a little bit different now than it was in the RSA days. And it really comes down to, do you feel like this do you want academic impact, or do you want to start a company and have a different kind of impact? And I think the happy medium, I think, Bill, is keep the basic technology open, and maybe it gets standardized, and then perhaps start your company and have proprietary optimizations, proprietary implementations. And I would say that that's kind of the path that I would follow. I don't know if I would ever start a company, but I would certainly follow the first part of it, which is publish the basics, put it out there for the world to use. And then if there's a company to be formed, well, use the technology as a base and then innovate on top of it, because there's just so much to do after that, and there's support, and it's so hard. You can't toss technology over a wall and think that it's going to grow trees, right? It's just that just doesn't work, right? So.
Yeah. It does need leadership, and it needs the academic leadership, it needs the business leadership, it needs people that understands the technology to know where it should be. And in academia, we see the seed, and the seed could grow into a big oak, but you need people that will translate that research into real impact. As you said, that's where you're hoping academia ends and industry picks up. And sometimes the route is through a spin out program, through licensing and so on. So you're right, there isn't a magical answer to this. So what do you think the next decade looks like in cryptography? Obviously, post-quantum cryptography is a big thing at the current time. We've got 10 years or so to get rid of all the stuff that we've used to build the internet. What do you think the next
Well,
10
yeah,
years looks like?
I mean, I think outside of post-quantum, I do think you're going to see deployment of much more sophisticated cryptography. I mean, I think blockchain has been a great thing for the applied cryptography community
Yeah,
and the theoretical cryptography community.
yeah,
Being able to point to ZKPs, being run in the billions, on Ethereum and other cryptocurrencies. So more of that. But I do think that what I would love to see happen is and this is something that I'm working on personally is we already have these enormously parallel GPUs and I think maybe combinations of CPUs and GPUs. I would absolutely love to see cryptography, a post-quantum cryptography on GPUs, but highfalutin, cryptography, not post-quantum encryption, not post-quantum signatures, but post-quantum ZKPs, post-quantum FHE, attribute encryption, all of those things. So I think the next frontier is going from cryptographic primitives to cryptographic protocols and deploying them worldwide, so individual consumers are using them. And like I said, I think the cryptocurrency space, the blockchain space, DeFi, decentralized finance space, has kind of pointed the way towards that, right? It's been a very motivating application domain. So
I completely agree. It's pushed the issue
yeah,
because it's at the highest levels of security and trust. Then it's really pushed the envelope and it's caused such advancement. Now wanting to see these primitives now being used in other areas, energy, transport, and so on, and they've just helped us build the primitives. And I suppose as you're right, you can actually see the primitives being built in homomorphic encryption at the current time. The lattice methods of the last 10 odd years or so were fairly pure, but now you're actually starting to see, as you say, attribute-based encryption as a possibility. You're seeing distributed signatures being created and a lot of good open source work. So I think you're completely correct about these 50 years of primitive building. We now have a new field. Now we can probably do it correctly with real hard problems, not the trapdoors of the past. So I think that's great. And if there's one thing you could have changed about your career, what would it have been?
Well, I think that's kind of an easy one. I would have started on cryptography, not in my late 30s, but my early 20s, right? I don't think I intersected with Shafi Goldwasser at
Mm.
Berkeley, because I think I sort of landed on or in the Berkeley campus, like about a year after she had left, and she and Sylvia had left. But we joke about that. But yeah, no, I think if I turned back the clock, I would have done a PhD in applied or theoretical crypto. There was only crypto back then. It was a small field back then, and it would have been a wonderful field to do a PhD in. But
Yeah,
it is what it is. I mean, there's no regrets here. I mean, it would have been a fun, different path to follow. But I think I ended up where I want to be, with respect to the aesthetics of the problems that I work on. And I'm a different person, now than I was, obviously much older, hopefully
yeah,
a little wiser than I was
yeah.
when I was a grad student. So, yeah.
Because you've obviously got this East Coast, West Coast thing with the US. You've got MIT on the east, cold winters, perhaps. And I've spoken to a few people who love the summers in the East Coast, but have went to Berkeley and Stanford and so
Yeah.
on because of the what's kept you in Boston.
So yeah, I mean, well, I have to say I saw snow for the first time when I moved here, right? And so I certainly wasn't used to the cold. But I have to say that I think just from a standpoint of the intellectual aesthetics, I do think that things have diverged, especially in the last few years with machine learning and to some extent blockchain. As well, the coasts have the Stanfords and the Berkeleys, put them in one bucket, have diverged intellectually from MIT in the following sense. And this is not meant to be a statement of judgment. I think there's MIT is still, I think the way it was, when I joined 37 years ago, where we want understanding of the fundamental issues. We want breakthrough technology. Patents. Whatever. The idea is where it's at. Let's get the beautiful idea, and then let's maybe let the Silicon Valley of the world run with it and deploy it. I think the proximity of Silicon Valley to the Berkeleys and Stanfords has certainly affected the way they think, and as Silicon Valley has grown, you see this sort of requirement of want of a better word, of near-term gratification, maybe not instant gratification, kind of permeating the research landscape, right? So that's the part that I think I'm very wary of, to not have my graduate students affected by the very near term potential for impact of the things that they work on, right? Sure, I love making prototypes. I love the fact that that research will get used, but you know what? Let's not compete with industry. Let's work on problems that that nobody's working on, or think of solutions that are disruptive, that no one would use them. But things change, technology changes, and in 10 years, maybe you did the groundbreaking work. I mean, it's not. I mean, it is groundbreaking in the sense that you're doing new things, but it's not impactful groundbreaking. And that only is realized, or the impact is realized in 10 years. So I would prefer to stay at MIT and have a long-term perspective. And it's not to say that you can't have a long-term perspective at the Berkeleys and Stanfords, but I do feel like there's the pressure from the outside. They get a lot more industry funding than MIT does, right? There's pressure from the outside to work on things that will help the next LLM, today, tomorrow, the day after tomorrow, or blockchain. And I want my students and my research group to be an enclave at some level, and have a buffer, between the real world and academic research, right?
Yeah. And do you think qubits is going to change your research? Do you think you'll still be working on bits
I'm Bill.
5 years?
I'm more worried about classical attacks improving personally, and breaking these number theoretic schemes than qubits. Not to say that I'm not worried about qubits, but if I'm worried about classical attacks, then I'm automatically kind of worrying about qubits. It's obviously a way worse in the qubit realm. Going back to what you said, one of the things that we talk about here is what is the next hard problem. Regev's learning with errors was really the most recent, and it's been a decade or more, most recent hard problem that has created this fountain of opportunity in cryptographic systems. And I think the theoretical cryptography community needs to come up with another beautiful hard problem that ideally a quantum computer can solve. And then I think suddenly you're talking about really groundbreaking work. That's like groundbreaking worlds of work, right? You've created a new world because now you have this new problem, like with learning for errors did. And then this slew of algorithms that are more efficient potentially, and also post-quantum secure, are going to come up. So I'd love to see that. I don't think I'm capable of thinking of that personally, but perhaps the students at MIT are, and certainly researchers at MIT are perfectly capable of this. But that's the type of, I think, disruptive work which would be hard to sell, and there's no instant gratification with that. You have to wait a long time to prove that it's an established hard problem. But you can work on wonderful protocols, new FHE protocols, new ZKP protocols, new indistinguishably obfuscation protocols based on this problem. And people are doing things like that. But you could lose because you picked a problem that is actually not as hard as you thought it was, right? So it's quite risky. But that's the type of work that I think people need to do. So.
And I suppose it's a problem for early career researchers now, because the demand is that they boost their H index and their I index, and they're publishing papers in journals and so on. So if they're not producing outputs, then they can maybe miss some promotions. So if you were a new researcher now, what problem would you like to work on?
Yeah, I think in some sense you have to have a portfolio with it's the is the diversified investment portfolio, right? And I do think that I think even students can do that. Now, obviously, you have to have a problem to work on, and I think mathematicians are a little bit different. I don't think of myself as certainly a mathematician, but even as a student, as a grad student, I worked on multiple things. Maybe 2 or 3 things. It has many I think positive effects. When you're stuck on something, you work on something else. You can multiplex. You're waiting for someone else to do what they're supposed to do because you're collaborating. You can do other things in the meantime. So I think you want to take risks. I think you should have a risky project. I think you'd have a project that is potentially groundbreaking. And I do think that you need to you can't graduate with 0 publications and expect to get a faculty position or even an interview. So you have to have the more incremental work that has publications associated with it. And so that's really what I encourage my students to do, which is think big, but also think small in terms of making progress, and see if you can break up this bigger problem into chunks, and perhaps you can publish the chunk even though you haven't solved the big problem. Maybe it's a career to solve the big problem and have impact, but it's progress to solve the piece of the problem, right? So it's fairly generic advice, and I think it needs to be customized to a particular student. But that's kind of roughly what I tell my students, right?
I totally 100% agree. You should have a big problem in your head. Every now and then you dip back into it, but then you're working on the day-to-day stuff so that you can produce your research outputs to show the incremental change. So I think you're completely correct. So if you were, this is my last question, I promise. So if you weren't a cryptographer and the inventor of PUFs and a researcher and so on, what would you have liked to have been as a career?
Oh, well, I mean, I don't know. I mean, I would like to be a championship level tennis player. I mean, I had dreams. I mean, I would watch Wimbledon. Growing up, and the Bjorn Borgs and John McEnroe, matches. If you'd only see the final, most of those first round and second round matches, you could only read about in newspapers. I think we finally got a TV in my household, right around the 1980 Asian Games, where in India, and that's when they were selling TVs, for fairly cheap, which were still pretty expensive, I think. I mean, that's partly. I mean, I know I don't have the genes or didn't have the nurture or the nature to be a championship level tennis player, but I do think I'd love to have a hobby that maybe it would have been bridge, maybe it would have been chess, but something that I got really good at, that I could have continued. One of my good friends, won a bridge tournament recently that was an open, tournament that was spread over days. and he's a really good friend, and I envy his dedication. He also has a company in the healthcare space. Worked for a while and is doing a startup with his son. So I think something like that, would be something that I would do. I think I'm happy with where I'm at, but it'd be nice to have a hobby that was I was equally passionate about, right, and that I could spend time on.
Yeah, yeah. So it's been a real privilege to speak to you today. So thank you for taking an hour and a half out of your very busy time. I've learned a lot from this talk, and I'm sure many people will have too. So keep up the great work, and I love your approach to research. And every early career researcher should be listening to the words that you're saying. So thank you so much, and hopefully we'll catch up sometime soon.
It's been a pleasure talking to you, Bill, and let's keep in touch. And thanks very much for inviting me to your podcast.
That's good. Thank you.